Okay, good afternoon once again. Let's get started on this session on Introduction to Data Science. Originally, we started this series as a introduction to data science, looking at different applications so that students are able to figure out what can be done, what is there, and actually the potential in available in data science. So for this week, we have Dr. Kaushalya Madhawa from Tokyo all the way. I mean, it's late evening for him. Thank you for coming and sharing this session with our students. Let me just give a brief introduction to Kaushalya. Kaushalya is currently a research engineer at LilyMed Technology Inc. Tokyo. He's contributing to the research and development for AI applications and novel medical imaging. Actually, that is why this topic is on medical imaging and deep learning. Right? And he has a PhD in artificial intelligence from Tokyo Institute of Technology. And his research interests include computer vision, metric learning, self-supervised learning, and medical AI. And before moving to Japan, I can remember he was part of the big data team at LearnAsia Colombo, and he has completed his master's at the University of Colombo School of Computing, UCSC. And we are proud to say that he's a product of Computer Science and Engineering, University of Moratuwa. Right, let me give it over to Kaushalya. We will have a kind of a brief session, and then we'll have a time for questions. And remember, we will also have at the end a very brief award ceremony for the data science challenge that we had as part of the series on Introduction to Data Science. Right, over to you, Kaushalya.
Okay, thank you, Dr. Shahan, for the introduction. So, I'm currently working as a research engineer at a medical technology startup in Tokyo. And so there I'm a member of the AI team that where we use different AI tools to solve problems in the medical imaging domain. Especially we are working on a new kind of medical imaging device for breast cancer detection. So, but I can't share too much details about that. So I will brief in this presentation. What I will do is I will go through different kinds of medical images and the current problems in those um, images and how AI can be used as some kind of solution to different kinds of problems. So let's start. I think all of you can see these images and
yeah,
okay. So, and I believe that everyone has, at least in some point of their lifetime, has looked at an X-ray for some routine medical procedure, or it can be a fractured bone or something like removing wisdom teeth. So it has become a part of our lives, and we don't question like how the life was before invention of these medical imaging technologies, right? So we use these X-rays is the most common one. So when we use these devices, they reveal internal structures in the body. So for example, you can see how the bones are, and if you have broken a bone, then it can be used to clearly see what has happened and how to diagnose that problem, and then a doctor will prescribe some medicine. But this was not how it used to be in 1800s or in earlier world. So if you go to a doctor and complain that you have some pain in the bones, and then the doctor will check by touching, and then like just by the feel he will say, okay, let's have a surgery and see what has happened. But in those days, like there were a lot of surgeries done because doctors don't know what's happening, going on inside the body. And so there were a lot of unnecessary surgeries were done, and there were a lot of like other kind of methods to find problems. So no one knows how if a person has tumor or not. So then a doctor will do surgery and then find out it's fine, totally fine. But yeah, that's how it was in 1800s and earlier world. So these days we have X-rays, CTs, MRIs, then PET scans and ultrasound. That I'm working on ultrasound data. So, and now we have a different kinds of doctors to look at these images and interpret what they are seeing, and then they diagnose the problems, and we call them radiologists. And all of these things started in 1895. Wilhelm Röntgen was doing some experiments with cathode ray tubes, and then he discovered using these cathode ray tubes, we can look at internal organs of the human body. So this was the first medical image that was ever taken. So this is the hand of his wife. And X-rays are used in all kinds of places for like finding out fractured bones or like lung images to check if a person has pneumonia, and then mammography that is used to find and diagnose breast cancer. That's also a kind of X-ray images. And so X-ray is a kind of radiation. So what it does is it goes through your body, and then at the other end you get illumination of how these bones are based on the dose of the X-ray. So in some cases, if the doctor can't have a proper diagnosis, then he will prescribe another X-ray or some other kinds of medical imaging. So sometimes they get 3 or 4 X-ray images based on different angles. And then, so X-ray was the main kind of imaging technology that was used for around 60 or 70 years. Then what's better than X-ray? So like in 70s, researchers found out that we can use multiple X-ray sources and get a lot of X-ray images. So CT, or we used to call it as CAT as well. So it is computed tomography. So as you can say from the name, it's like computers are involved in this. So what it does is, then there is an X-ray source, and it can revolve around the body or the body part where you want to take images, and then it gets a lot of measurements. And then using computers and image reconstruction algorithms, then we get an set of images. So these are different slices. So this is a CT scan of a human brain. So instead of one image, now we have a lot of images. Like in some cases, it could be 50, 60, or hundreds of images. And so earlier we had only one X-ray image, and if we couldn't, doctor couldn't figure out, then he will take another X-ray from a different angle. But now using these kind of technologies, we get a lot of images. And so if you put one of these images on top of each other, then you will get a 3D volume. So so this height, width, and then there's a depth. So this becomes a 3D volume of images. And then this 3D volume is constructed using image reconstruction algorithms. And then I will show this is another different kinds of medical imaging method. So like X-ray and CT use the same kind of technology as the imaging. So it uses X-rays. And a problem with X-ray is it uses ionization radiation. So X-ray at higher doses can be considered as carcinogenic. That means it can cause cancer. So taking a lot of X-rays is not advisable, and especially if a doctor needs to take an image of a brain. So in most of the cases, rather MRIs are used. So MRI works like this. So the patient goes inside a powerful magnetic field, and then there is a electromagnetic signal. So you can watch this video later and find out how it works. And then it creates the image based on how protons, that means because human body is made of water, H2O, so it has hydrogen atoms that are protons, and they are excited when they are changed from when there is a external electromagnetic force, and when it's removed, then it changes its direction. So it's measured using these devices. And because it doesn't use any ionization radiation, so it doesn't have that problem with X-ray. So we can use it on brains and in other places where using CT is not prescribed. And then there is ultrasound. So this is a different one. So X-ray and CT uses X-rays, and then in ultrasound it uses sound waves. So it's completely safer than previous ones. And so it's like this. So like we have acoustic, that's our hearing a range of sound waves, and then at higher frequencies we have ultrasound signals. And so you can see this is an ultrasound scan taken from a handheld. So there are different kinds of ultrasound devices. And simplest ones are called handheld ultrasound. So I think most of you have seen them. Like a doctor keeps it on the skin of the patient and then looks on a small screen like this. And then there is this called ultrasound computed tomography or USCT. So this is a combination of both ultrasound and CT. So this is the kind of devices that I'm working on. So instead of one receptor, so it has like multiple receptors. So this is similar to CT, but with ultrasound waves. And so if the patient's body part is here, then there will be a lot of waves going on, and then they reflect. And we take a lot of measurements, and then again using image acquisition algorithms, then we create a set of images and image volumes. So we have looked more at most of the popular methods. And next, like earlier the radiology started with X-rays. Now we have CT, MRI, USCT, all of them consist of like volumes of images, not just one image. And in most of the cases, patients they don't have a disease. So we can't say like all of the people, like they are not, they won't have illnesses. So like, it's like looking for a needle in a haystack. A radiologist has to go through like thousands of images to find one abnormal incident, and it is very, very tiring process. And now radiologists have much more workload because of the abundance of data. And so if we call someone, if a doctor says someone has a disease, and in reality that he doesn't have the disease, so that we call false positives in data science and machine learning terminology. And so if someone gets a false positive diagnosis, then a doctor will prescribe more scans, or sometimes it will lead to biopsy or different kinds of surgeries. And then the patient has to go through unnecessary interventions, and then it costs a lot of money and time, and it's not stressful as well. So now we'll sorry, my display is, give me a second. Okay. Now we look at different medical imaging devices and the challenges that we have, and how can we improve it using computer vision and different kinds of machine learning and data science tools that we know. So now let's look at computer vision and where the state of the art is. So computer vision, what is it? So what it basically does, it interprets images and visual things that we perceive using cameras and other kinds of sensors. So earlier days, we had different kinds of algorithms for computer vision, and then for segmentation. Then natural language processing had its own kind of algorithms, but now with these deep learning technologies, now we have like same kind of algorithms used in different kinds of modalities of data. And so basically, these are some simple tasks that are done using computer vision. And so first, the simplest one is image classification. So given an image, the model will say if there's a cat or not. And then the next one is object detection. So given an image, identify what are the objects in that, and then highlight them using a bounding box. And okay, there's this tower and information about that. And then the next one is segmentation. So image segmentation means I find boundaries of different objects and then assign each pixel into that object. So this kind of okay, and yeah, sorry, my display disconnected. I think now you can see it. So image segmentation is used frequently in autonomous driving applications. So if you look at Tesla, on especially these companies that use computer vision and cameras to sense what they see. And so in those cases, they sorry, I think I had to reshare it. Okay. I hope now you can see the slide.
Yeah, we can see. Thanks.
Okay, sorry. Yeah, so I was talking about these like 3 different problems, most popular problems in computer vision. So like image classification, object detection, and image segmentation. And then we know deep neural networks are used everywhere. So earlier days, we had different kinds of algorithms for different kinds of problems. Like for image segmentations, we had snakes and then parametric methods. And for object detection, then we had different kinds of handcrafted features. So we create features and then train a simple SVM or some kind of kernel machine. And then for another problem, then there were like a complete different set of algorithms. So we had to learn all of these things. But now everything has become simpler with deep learning. So what deep learning has done is it's kind of like expressing different kinds of problems in a simple, like similar template. So if you look at the simplest way to explain deep neural network, so it's like this. So you give, like in computer vision, you give an image and then ask it to classify what it sees. So in image classification, it should say, okay, so this is an deep neural networks because we call them deep because there are multiple layers. So this is a simple one. So like there are in some networks, there are like 50 or hundreds of layers like this. And each of these layers are made of weights, and these are some floating point values. And that we learn using an algorithm called backpropagation. So what it does is we give an image and then it predicts, okay, this is a cat or a dog. And so let's say we give this image and then it predicts 40% as cat, dog and 60% cat. So there's, obviously you can see there's an error in the ground truth that we want to see and what it predicts. And so the difference between the ground truth and what it has predicted is called loss. And we want to minimize that loss. So that means we want the model to be correct on all kind of inputs that we have a label. So we call like each of these image has a label. So we feed these images with their labels, and then we train the model using the algorithm called backpropagation. So what it basically does is it calculates the loss. So based on the ground truth, and so it's the difference between what we want to see and what we predict from the current model. So based on the loss, when we tune these model parameters, and so we keep training the model, and then what we basically do is we look at the loss function. So this loss function means how the loss changes over time. And so we keep training it, and then we get a trained model at the end. What made these neural networks so popular these days? One is we could get rid of like handcrafted features. That means like early days, then we had to create a different set of features for dog classification, and then for medical images, then we had to look at different kind of features and based on the domain. And so there is no place for like this kind of handcrafted features in this. So the model learns features itself based on the labels and the input. So our life is easier. And so all you have to do is we find a model and then keep training with a lot of label data. And another thing is we can tune or the train model on one set of data set and then train on a different task with less effort. We call it transfer learning. So I'm not going into details of this, or it's a different, it will be a different lesson. So you can find a lot of content on these links I have added there. And so these are like basically most popular deep neural network types. And it started from multi-layer perceptron. So these are used for more like tabular kinds of data. But when we look at images, images have a 2D structure. So like if you get an image and then flatten it, that means you take these images, pixels one by one, and then you make a long list, then it will lose some of the information, the semantics of the image. So there we use convolutional neural networks, and especially deep learning became popular because of the success of convolutional neural networks in 2012, partially based because of the GPUs. So we train these models on GPUs, especially using CUDA, or then there are a lot of libraries like PyTorch, TensorFlow, and JAX. So it has become quite easy to train these kind of models. And so we use these convolutional neural networks for learning from image and visual data. And then there are recurrent neural networks that are used to learn from temporal data, and they were quite famous for used in natural language processing applications. But now then this transformers is a quite new kind of a neural network, and it's completely based on attention architecture. So it can compute some kind of similarity between each and every data point. So this completely changed how natural language processing was done. And this was developed by Google Brain. And now you can see transformer architectures used almost everywhere in natural language processing. And now it has been used in some computer vision applications as well. So there's a lot of things happening in neural networks, deep learning field. So now let's look at how we can use deep learning for medical imaging and what are the problems that we can solve using this kind of deep neural networks. So the first one is let's start from image reconstruction. So we get a lot of data points from the receivers in those medical devices, as you saw in CT or the USCT, then MRI. And so these devices were made in 70s, 80s, and these algorithms have been handcrafted, but they work fine. So one thing we can do is, if we can reduce the time a patient spends inside this machine, then it will save a lot of cost. And especially if you look at MRIs, they are really noisy. And USCT is also slow compared to some other machines. And so it's better if we can make it faster, but without reducing its accuracy or how we see the images. So now there have been several algorithms that use deep neural networks. So this is an initiative started by Facebook and NYU. And in their work, they show that deep neural networks can be used to make this image reconstruction part up to 10 times faster compared to a traditional MRI reconstruction. And then there are a lot of other algorithms for segmentations. So, that means like you want a medical image, identify different parts of organs, and then that makes the work of radiologist easier, so he can get this information and do diagnosis easily. And then the tumor detection. Tumor detection means you give an image and then the model will say, okay, this part has probability of being a tumor. So this is an image from a mammogram, and this research was also partly done by Google. And so we have these object detection type of models to detect tumors in mammograms and lung scans as well. So deep learning has been used in a lot of these radiology applications, and in most of the papers they show that they are quite successful and sometimes they are better than radiologists. But the real problem is, like, if someone reads all these papers and news articles, someone can think, okay, like, do we really need radiologists, because these models are doing their job better and like for free, almost for free, because like they don't take much time as a radiologist. So we see a lot of articles like this, like Google's new AI is better than radiologist, and then sometimes they say it's better than this much amount. And in 2015, Jeffrey Hinton, who is considered as one of the fathers of deep neural networks, and who won Turing Award in 2018, told in 2015 that we should stop training radiologists now. It's just completely obvious within 5 years, deep learning is going to do better than radiologists. And here we are in 2021, so still we have radiologists, and in most cases, radiologists are overworked, and we need more radiologists than the number of radiologists we have, especially in developing countries. And so, what are the challenges in using deep neural networks in medical domain? So, one problem is high labeling cost. As I told you earlier, that we need to have labels to train the model. So we don't get labels for free. So someone has to label these images as, okay, this image has a tumor and where it is. And this annotation takes a lot of time. And especially in medical images, we can't ask random people on the internet to label few hundreds of X-ray images. We have to ask especially qualified doctors to do that. So, and there are radiologists who are specialized to look at X-rays or CTs, MRI. So we have to find the right type of radiologist, and then we ask them to do the labeling. And this is a really expensive task, and it takes a lot of time. So that's one of the major problems we have right now, because like unlike natural images, or doing autonomous driving, where companies hire a lot of people to do labeling. We can't hire hundreds of doctors, so it costs a lot of money, and we don't have that many doctors with enough qualifications. And then the other problem is, like, if we create labels, then we have different problems with the same kind of data. Then we have to create another set of labels. And so it keeps growing the task that we want to do. And so to get good results, we need high quality data, and a lot of high quality data is useful. And another problem is robustness of these neural network models. So here I have shown one example that was shown in a previous paper, where if you add some noise to an existing image, then the model will classify it as completely something random thing. So here you add a noise to a panda, and then it starts predicting as given. So there are robustness and uncertainty problems. So we can't completely trust some of these models because we don't know why it predicted this image as a tumor or this with this problem. And so then we come to this the same problem, interpretability. So if it, so unlike saying this image is panda or gibbon, we want to know why your model predicted this X-ray as a tumor, because we can't just trust it. So that's one research direction. Like there are a lot of workshops and events are happening around this problem, model interpretability. Like how to interpret the model, like why does it predict in this way? Like if a doctor says, okay, you have this disease, he has some kind of reasoning, like causal reasoning, okay, you have this problem and we have observed this in these many patients, or because of this, there's a high probability of you having this problem. But there's no such thing at that level for neural networks. And then there's data bias. So in if we train the model on Europeans, like a large population of Europeans can use the same model on Asians or some other population or like some other uh, gender or like weight. So these lot of things are different from the population. So we need to have a lot of data, and modeling these kind of data biases can be complicated. So because of that, it's better to use both models as well as radiology. So instead of replacing radiologists, what we will be seeing in future will be, we will have models and radiologists. So radiologists will be using AI tools as one of their tools to make their work easier. So they will get the predictions of these models and then look at different other modalities, and then they make their decision. So model won't be making the decision, but they are helping the job of the doctor. And so I talked about the cost of labeling. And another problem I forgot to tell was we have to train the doctors to use these labeling tools. So I have seen how it works. Uh, uh, we have doctors to label medical images, and so they take some time to train to use these labeling platforms and to understand how to label these things and annotations. So training takes a lot of time, and doctors are good at diagnosis and doing their thing, so they usually write medical reports. But then to get labels, we have to train doctors to use different kinds of labeling tools, and then we have to pay them to do this job. So instead, if we can use the medical reports that they have already written to train models, instead of asking them to label, then it will make these training pipelines easier, and then that gives us much more data. So we can use existing data as well. So this model is called CLIP. So this was developed by OpenAI this year. Instead of getting a label for each image, or like in image classification, what we do is we give this image and we give the label dog, and because someone labels this image as a dog. Instead, what we do is they got images and then some sentence describing the image from websites. And then they train these models, so there's text encoder and image encoder. So they get features from image and features from the text. And then they train a single model using both text plus image. And then they use it for classification. So if you can use these kind of models for training on medical imaging, that will make it easier to get data, and we will be able to get a lot of data for training. So I have seen some research on this direction. So there already are some models trained on medical images, and their text descriptions written by doctors. So this was some fun demo I did. So I took a clip model and then I got a data set of radiology objects. and then kept training it on a cluster of TPUs. So like I didn't have like millions of images as this OpenAI had, because it's difficult to get medical images. In some cases, we have to register for different websites, and then we have to do some ethics courses and fill different kinds of forms, and then wait until we get the data sets because of privacy issues. So what I did was I took the clip model and trained on these medical images. It started to learn high-level features, like if I search the model with queries like ultrasound scan or PET scan, it was correct in most of the cases, but still I couldn't get it to give me images if I search for a certain kind of tumor or a brain image. So I think it needs more data to be trained. And so this comes to an end. So I hope you got something out of this presentation. So I didn't go into any of the details, and this is a brief overview of different imaging technologies and how deep learning can be used. Thank you. So do you have any questions?
Yeah, thank you, Kaushalya. Yeah, we can ask questions. Either you can unmute yourself and ask, or we can use the chat to ask the questions.
Dr. Kaushalya, in terms of using tools to create machine learning models for image like object detection, what do you think is the most advanced tool that we can use? Something like darknet?
Sorry, I didn't get your question. Are you
There
asking
are a
about
lot of tools that we can use to create object detection models, right? So an example like something like using darknet with YOLO v4. So what do you think is the most advanced one that we can use for this type of scenarios where there will be different sizes of objects also, right?
Yeah, so it depends on the problem. So like object detection models work on these images as well. So you can use off-the-shelf models like MassCap CNN or FastCap CNN. So they will work, but then you will have to do some fine-tuning on these models because these images, like especially these objects, can be smaller, and then they are like the same class of objects will have different shapes and different structures. So still you can use the same set of object detection models, but so that is for 2D images. And in some cases, so if you are classifying CT or MRI images, then you will have to use 3D convolutional neural networks. In that case, using object detection models can be too expensive. So there you have to break the process into two. Like first classifying whether this volume of images has this tumor or something, and then use another model to predict where it is, or like segmentation. I hope I answered your question.
Yes, thank you.
Is it?
There's a question on the chat, Kaushalya.
Okay. For images, I can't say for sure why we need transformers, but there's one thing is like it makes easier in those platforms. So if we have one kind of algorithm, and so now I have seen some research that's showing transformers work well on medical images rather than on natural images, because if you take natural images, then there can be all kinds of scenarios. So to get the CNN level performance for like images like from ImageNet, then they had to train on large sets of data, ImageNet 21K or like larger sets of images, because like in CNN we have this bias that CNN has been defined for image recognition, but these transform models don't have such bias, so it has to be learned from the data set. So there we need to have a lot of data, like very large data sets. But for medical images, it works well, I mean, up to the point, like similar to CNNs without that much data. And another thing is there are some models like DETR data, so they work well. And one problem with object detection models is they are sometimes complicated. So they have this ROI polling and then different kinds of things. So data makes it simpler using transformers. So at this point, I don't see any point in using transformers over CNNs, but it depends on the data set. So, but there will be newer models, faster and better models in future.
I have a question. I'm a radiologist affiliated with the Colombo Medical Faculty, and I'm working with actually a team in Murto University regarding one thing is we are doing liver volumetry, and we are trying to use AI for liver segmentation. My question is actually one of the challenges we have is analyzing the segmentation in moving image, because ultrasound is using ultrasound. And when there are respiratory movements, is there any sort of, I mean, obviously I don't have the technical know-how. What I want to know is what are there sort of AI tools which we can use to analyze and do segmentation in moving, in the sense respiratory movements of the liver. So can we sort of use the images, which sort of you get a series of images, as you can imagine, when the person breathes.
Yeah.
Are there any algorithms for that?
Okay, so you mean like the artifacts that you see in images due to the moving of the organ?
Artifacts. For example, the liver, what we want to see is the liver. Now, for example, liver, we can't see the full extent of the liver when we keep the probe on the person, right?
Yeah.
So one way of getting the full extent of the liver is asking the person to breathe in, which pushes the liver down. Obviously, but then you will not see the lower part, because now the lower part would have moved away from the what do you call the field of view. So what we want to do is sort of fuse the lower part and upper part and get the full image using the video of the that we are going to obtain. That's the challenge that we have at the moment.
As I get from the question, is it correct? Like, is it same as getting like one image based on different measurements taken at different places?
Yes, same, more or less the same, yes.
Okay, so you are trying to, so this problem is called, like one thing you can do is image registration. So it means like you have two images taken at two different angles or two different places. So it creates a mapping between this pixel in this image. So you can use image registration techniques to identify where those images should match, and then you can create one image by image tree in that way.
Okay. Thank you. Okay.
Do we have any other questions? Or else we can close the session. while we are waiting for the questions, Kaushalya, this the reports that you talked about, they were. I mean, did you have to go into hand written text recognition also, or was it already digitized?
It's digitized. So this data
Okay.
is taken from medical journal papers.
Oh, okay.
They have the text and the
Straightforward.
image. Yes.
So, Kaushal, you still think we'll need radiologists, right?
Yes. Yeah. I won't totally trust AI models, but
Okay.
there's a use, like hybrid kind of models will be useful.
Okay. Actually, I invited a few. This target mainly for engineering. We invited a few people from the medical faculty. Kaushal, you know that we have a medical faculty now, right?
Yes, I heard like it
Okay,
started
okay.
this year. So
Yeah.
nice.
Right. I think going forward, maybe if there's any collaborations that we can have with you, maybe we can think about how we could go about in doing that also. Right. Okay. So if we don't have any other questions, we can conclude this session. As I said, I need a few minutes to just announce the winners of our data science challenge. And before that, let me thank Kaushalya for sparing the time with all the other work that he has to do, and for sharing his insights and experience in the area of artificial intelligence and data science. Thank you, Kaushalya, and hopefully we'll be able to get you to join us in the future with similar sessions. Okay, so our session on the introduction to data science is over, and most probably this will be our final session in the series, and we want to conclude it with by announcing the winners of the data science challenge that we had we conducted as part of this series of sessions that we had. Right, so let me get into that and conclude it. Yeah, I would like to thank Dialogue for sponsoring this data science challenge. Let me, for the benefit of people who are new and for the first time here, let me explain. We gave a data science challenge. Maybe some of you may be familiar with that type of challenge that we do, where we gave a data set for the students or the participants to build a model, a training model, similar to the models that Kaushalya was talking a few minutes ago, right? And then we had the answers for the, for a part of the data set where we did not give those answers to the students, right? So the objective was to build a model, train the model, make sure that you remove everything that Kaushalya was talking about a few minutes ago and try to be the best, right? Try to get onto the top of the list. And so that's the challenge that we gave, and there was quite a bit of interest and a lot of submissions. And at the end, we took the best 3 people on the leaderboard, because if you can remember one of the sessions, it was Yudhanjay who said that it should not always be accuracy only, right? So, sometimes we go for accuracy. I mean, accuracy gives us a indication of how good you are, how good you are doing. Right, so what we did was we got the top 3 teams, and that was part of the rules of the competition anyway, and then asked each group to give us a presentation of what models they used, how they went about, what type of reproducing they did, and things like that. Right, so it was a very short presentation, and then we got a panel of lecturers, resources from the Department of Computer Science and Engineering and Data Research to evaluate, and then we do have the final results today. I hope the people are here. Anyway, they can get to know. Right, so Dialogue sponsored, and for the top 3 top team, they will allow them to buy some devices to the value of about, I think, 3,000 rupees or 5,000 maybe. I can't remember. Anjana, you can correct me.
So, they'll be giving me a MiFi device per person.
Yeah.
Mobile Wi-Fi hotspot.
Okay, we'll give you the details. But anyway, I think the most important thing is to get to know who the winners are. Right. So let me very quickly go through the winners. I'll start from the third place. So we do have the third place. The team clusters, and let me read the, 3-member teams. We asked for 3-member teams. So Purna Escure, and then we have same team. We have Bandara WRHM, and we do have Jayavira IGHI from the team clusters. That is the third place, and then we do have the second place. Now you would guess what the first place is. Ranasingh AI from Jade, and then we have Ratnasiri KKDA of the same team, and then we have Lianage ISM. Right, and then the top team is XG Boosters. XG Boost is the kind of an algorithm that a machine learning algorithm that they have used that same name for their team, right? Vibhushan, and we have Vardarajan, and then we have Tuakaran, right? So from XG Booster. So let me congratulate the top team for spending a lot of effort and somehow getting to the top. I think they were the top in the leaderboard also at the end of the competition, and deservedly they were able to convince our panel of judges that what they did was sound, and it's not a fluke that they got to the top of the leaderboard. Right, that concludes our session, and yeah, we can close it here unless there are any questions from the students regarding the challenge or any other thing regarding what we did as part of this collection of sessions to introduce data science and show some of the applications that are available. Okay, we can close the session.